Question 4. So we're told a sample of strontium R is known to contain strontium oxide, strontium carbonate, and some inert purities. To determine the mass of the strontium carbonate present, a student weighed a sample of the solid R and then heated it in a crucible for 5 minutes. The sample was allowed to cool and then reweighed. This heating and cooling is carried out 3 times, and the results are given to us in the table below. We've got the mass of the crucible, the mass of the crucible and the R, the mass of crucible and sample after first heating, second heating, third heating. So we can see that after 2 heats, or 2 lots of heating, the mass is constant. When strontium carbonate is heated, it decomposes, so it breaks down according to the following equation. We've got strontium carbonate producing strontium oxide and carbon dioxide. We need to say why the mass of the solid changed during the experiment. So looking at those 2 products, particularly carbon dioxide, we know carbon dioxide is a gas, and so it's likely that that carbon dioxide gas has been lost to the surroundings, most likely. Now the next bit then, we're asked to use the data in the table to calculate the mass of strontium carbonate specifically in the original R sample, giving our answer to the appropriate precision. So, there's quite a bit going on here then. We've got this table, we've got a lot of information on it. Now, we're trying to work out the mass of strontium carbonate. Now, looking at our data, that's really difficult for us to do because, well, just from what we've been given straight away anyway. We've been given the mass of the crucible. We could work out the mass of the R, but that would be quite difficult. It's going to come down to this equation, so I'm just going to rewrite that on this page. Strontium carbonate produces strontium oxide and carbon dioxide. Now, what we can work out reasonably easy is the mass that has been lost. Now, if we assume all of that mass lost is carbon dioxide, so we can start with that then. If we've got a beginning mass of 16.11 grams and it ends up as 14.58 grams, then we can say that 1.53 grams of carbon dioxide have been produced. Now, that's where we can come back to our equation, because if we know that 1.53 grams of carbon dioxide has been produced, we can work out the mass of strontium carbonate. So I'm going to do this using a table. You know how I like a table. And I'm going to put in it space to calculate the mass, the molecular mass, and the number of moles. Now, I don't need to work out strontium oxide, so I'm going to get rid of that. And I know that my mass of carbon dioxide is 1.53 grams. I can then work out the molecular mass of both of my substances. So strontium carbonate should be 147.6 and carbon dioxide is 44. Leaving me with a number of moles. Well, if I take the mass of carbon dioxide divided by the molecular mass of carbon dioxide, the number of moles of carbon dioxide is 0.0347. I'm going to keep that on my calculator. Now, looking at the ratio of strontium carbonate to carbon dioxide, it's 1 to 1. So if there's 0.0347 moles of carbon dioxide, there must be the same of strontium carbonate, but I've still got the same number on my calculator. I then need to multiply that by the molecular mass, which leaves me with a mass of strontium carbonate of 5.13 grams. That will be my final answer in this case. Making sure it's at an appropriate precision. Well, how did I get that? Looking at my table of data, I can see that the smallest number of significant figures is here, 9.85. So I'm going to keep it to 3 significant figures, which gives me 5.13 grams. Quite a lot of marks there when the method is actually not overly difficult. It's about thinking about what information we've been given in the question. The next one then, I have to work out, so I've been given the uncertainty of the balance. I have to calculate the percentage error in the initial mass of R used. Now, to calculate the initial mass of R used, we've got a way by difference. We've got the mass of the crucible and the mass of the crucible and the R. So we've got two values. So the actual error here would be plus minus 10 milligrams. What I am going to do here then is looking at my calculations. So I've got mass of crucible is 9.85 and the mass of the crucible in the R is 16.11. So I'm going to do 16.11 minus 9.85, which gives me 6.26 grams of R. Now, there's two things I can do here. I can either convert 6.26 grams to milligrams, or I can convert my milligrams into grams. I'm going to convert my 6.26 grams into milligrams, so I'm going to times that by 1,000, which gives me 6,260 milligrams. Now I want to work out the error in that then. So I've got an error of 10 milligrams divided by 6,260 multiplied by 100, which gives me a percentage error of 0.16%. The next question then, if I can turn the page, we're told that the mass of inert impurities is 347 milligrams. We need to deduce the mass of strontium oxide in the sample and justify any assumptions made in calculating your answer. So we just calculated that there was 6,260 milligrams of sample. We're told that 347 milligrams are impurities, and in our previous answer we calculated that there was 1.53 grams, sorry, not 5.13, my apologies, 5.13 grams of strontium carbonate. So if I convert that strontium carbonate into milligrams, we've got 5,130 milligrams, and so that subtraction tells me there is 783 milligrams of strontium oxide. Now the assumption I've had to make here then, looking at my table of results, is that all of the strontium carbonate has been turned into strontium oxide and carbon dioxide. And the reason I can make that assumption is because we have reached a constant mass. So we're assuming that all the strontium carbonate has reacted as constant mass is reached. The next bit then, strontium metal can be extracted by heating strontium oxide with aluminium metal. In this reaction, strontium vapour and solid aluminium oxide are formed. We have to write an equation for the reaction and state the role of the aluminium in this process, explaining why the strontium forms a vapour but aluminium oxide is formed as a solid. So, if we need to write an equation here, we're going to have to look at what the reactants we're starting with. So we've got strontium oxide. Now I need to be able to work out the formula of strontium oxide. So looking at my periodic table, I can see strontium is in group 2, oxygen I know to be in group 6. So the formula here then is going to be SRO. I'm reacting it with aluminium to produce strontium vapour, which is going to be SR, and solid aluminium oxide. So aluminium, group 3, oxygen, group 6. So the formula of aluminium oxide is going to be Al2O3. So now I've got those formulas, I can put those into an equation. So I've got SRO plus Al will give me SR and Al2O3. I then need to balance that. So looking at that, I've got 2 Als, so let's make that 2. I've got 3 oxygens, so that would be a 3 with 3 SRs. The role of aluminium then, looking at this reaction, I can see that I've got SR combined with O producing elemental SR. So I can look at the oxidation states here then. So O always being -2 means that SR is going to be +2 and it's going to be changing to 0. So I can see that SR has been reduced as it's gained 2 electrons. Now because of this then, the aluminium is acting as the reducing agent. Now we also have to explain why this strontium is a vapour, whereas aluminium oxide is a solid. So I'm going to need to compare the type of bonding within those two substances. Well, Al2O3, I've got a metal and a non-metal, so I'm going to have an ionic bond, and it's actually going to form a strong ionic lattice. So these bonds are very strong. Comparatively then, the SR will form metallic bonding. Now generally metallic bonding is very strong. However, comparatively to the Al2O3, it's relatively weak. Meaning that that structure is more likely to be a gas than the aluminium oxide.